Hi, in this video, we will review Bayes' rule and discuss a few data science interview questions related to Bayes' rule. First, take a look at the question. 1 in 1,000 people have a particular disease. The test is 98% correct if the person has the disease, and the test has an 1% error rate if the person does not have the disease. If someone tests positive, what are the odds they have the disease? So this is a very classic Bayes' rule problem. We will solve it in a minute. Let's first review Bayes' rule. This is a definition. Suppose C1, C2, all the way to Ck are disjoint events whose probabilities are not zero and add to exactly 1. Then if A is any other event whose probability is not 0 or 1, then we can calculate probability of Ci given A using this formula. So let's first understand what these C1, C2 all the way to Ck are. So they are disjoint events, which means the intersection of any two events is empty. So we can use this notation to denote it. Ci intersect Cj is empty for any I and j where I is not equal to j. And secondly, their probabilities add to exactly 1. Okay, so which means the union of all of these events is exactly the sample space. So we can write the union I is from 1 to k, Ci is equal to the sample space. Okay. So together, that means C1, C2 all over to Ck is a decomposition of the sample space. And A is another event which is not empty and not equal to the sample space. So A is not empty and A is not equal to the sample space. And then the probability of Ci given A is equal to P of A given Ci times P of Ci divided by the summation of P of A given Cj times P of Cj, where j is from 1 to k. So let's briefly derive this formula again, and so that we can also better understand the meaning of Bayes' rule. P of Ci given A is equal to probability of Ci intersect A divided by P of A. This is the conditional probability formula, right? And then we can rewrite the numerator using the general multiplication rule. The numerator is equal to P of A given Ci times P of Ci. And the denominator is P of A. And P of A can be rewritten in this way. P of A given C1 times P of C1 plus P of A given C2 times P of C2 plus all the way to the last event, P of A given Ck times P of Ck. So the denominator actually uses a rule which is called law of total probability. And the numerator uses a rule which is called the general multiplication rule. And what is the purpose of this Bayes rule or Bayes theorem? So apparently, originally, these Cj's are conditions. Right? We know P of A given Cj for some j. So suppose we know all of these conditional probabilities, and we also know the marginal probabilities of all of these conditions. Then can we reverse the roles of the event of interest and condition so that we can calculate the probability of a certain condition occurs given the event of interest has occurred? So originally, Ci's are conditions, and A is event of interest. So we have a bunch of conditional probabilities like this, and also we have the marginal probabilities. So given this piecewise information, we want to know, given A already occurs, what is the probability that some condition Ci occurs? So we essentially reverse the roles of condition and event of interest. So this is the beauty of the Bayes rule. So now let's go back to our interview question from Amazon and try to solve it. 1 in 1,000 people have a certain disease. Let's use D to denote having the disease. Then probability of D is equal to 1 over 1,000, which is 0.001. Then the second sentence said the test is 98% correct if the person has the disease. So this is a true positive rate. The person has a disease and the test gives a positive result. So probability of positive given D is 98%, so 0.98. And the test has an 1% error rate if the person does not have the disease. In other words, the test will give a positive result if the person does not have the disease. So this is a false positive rate. So the test result is positive, but the person does not have disease. We use D to the C, D complement, to denote the event that the person does not have the disease. Is 1%, so 0.01. Now let's see the question. If someone tests positive, what are the odds they have the disease? So you see the event of interest and the condition are reversed. The event of interest is the test is positive, right? But now it is given. It is a condition now. And we want to know what is the probability that they actually have a disease. So we want to answer this question. Probability of having the disease given a positive result. Okay. Now let's apply the Bayes rule. P of D given positive is equal to, so by the way, in this question, there are only two conditions, D or D complement. They also form a decomposition of the sample space, right? Because D and D complement are disjoint and the union of them is equal to the sample space. So the condition is satisfied. So let's apply the Bayes rule. The numerator should be P of plus given D, you reverse the rows, and then times P of D. In the denominator, one of the terms is always equal to the numerator. So let's copy down the numerator. Then plus the other case, P of plus given D complement times P of D complement. So pay attention. The denominator is P of plus. So the event in both of these two terms should be plus, should be positive. Okay? Don't be confused. And then let's figure out the numbers. P of positive given disease is 0.98, which is given. And P of D is also given 1%. Sorry, 0.1%, 1 out of 1,000. So 0.001. And denominator, the first term is the same with the numerator. And then what is P of plus given D complement? This is exactly the false positive rate, which is 1%, 0.01. Okay. How about probability of D complement? Because P of D is 0.001, P of D complement is equal to 1 minus P of D using the complement rule. So is 0.999. 1 minus 0.001. Using a calculator, or you can use R as a calculator, you see that is equal to about 8.93%. All right, this is how to solve this problem. Okay. So you see the key is first, identify the information that is given. Write down the probabilities and conditional probabilities that are given. And then figure out the question we want to answer. Then apply the Bayes formula. Pay attention to the denominator. Also pay attention to the decomposition of the sample space. You have to be very clear what are the conditions that we are considering. In this case, either D or D complement, right? There must be a decomposition of the whole sample space. All right, now I see a challenge question from Microsoft. 3 friends in Seattle each told you it is raining, and each friend has a 1/3 probability of lying. What is the probability that Seattle is raining, assuming that the likelihood of rain on any given day in Seattle is 0.25? Again, if you want to solve this problem by yourself, you can pause the video and then resume a little later. Now let's solve this problem. So first write down the information that is given. So 3 friends in Seattle each told you it is raining. Let's use some letters to denote the 3 friends, respectively. Let Y1 be the event that the first friend said it is raining in Seattle. Okay? And then Y2 will be the second friend said the same thing. And Y3 is the third friend said it is raining. Let's use R to denote the event that it is raining in Seattle. Then let's write down the probabilities that is given. Each friend has a 1/3 probability of lying. So that means probability of Y1 given it is not raining in Seattle is 1/3. And it is the same for the other 2 friends. So we can write in this way. There is another case. If Seattle is raining and your friend told you that it is raining, then your friend does not lie. In that case, the probability is 2/3. And again, the 3 friends have the same probability of not lying. And finally, we also know that the probability that Seattle is raining is 0.25. And we want to know this probability. What is the probability that Seattle is raining if all of your 3 friends told you that it is raining? So you want to answer this question. P of R given Y1 intersect Y2 intersect Y3. This is a question you want to answer. So let me add a page. So P of R given Y1 intersect Y2 intersect Y3. So for now, let's treat this as one single event for convenience, and then we can separate them a little later. Now let's first apply the Bayes rule. P of Y1 intercept Y2 intercept Y3 given R times P of R divided by P of Y1 intersect Y2 intersect Y3 given R times P of R. So the first term is the same with the numerator, and the second term is, again, the event should be the same. Y1 intercept Y2 intercept Y3. And then the condition changed from R to R complement. So it's not raining in Seattle. So this is the Bayes rule. Now we need to calculate the probability of Y1, Y2, Y3 given R and Y1, Y2, Y3 given R complement. We can assume that the 3 friends' behaviors are conditional independent given R. So this is reasonable. So in this case, we can rewrite the numerator as P of Y1 given R times P of y2 given r times P of y3 given r and times P of r. Denominator, same. Okay, we can copy this and paste here. Okay. And then plus P of y1 given r complement, P of y2 given r complement, P of y3 given r complement, together times P of r complement. And what is P of y1 given r? So that is probably that your first friend does not lie. So the probability is 2/3. Okay. And the second and third friends have the same probability of not lying. So 2/3 to the 3. And then times P of r, 125. Then the denominator, the first term is the same with the numerator. And then the second term, probably that your friend lies is 1/3. So it should be 1/3 to the 3. And times probability of is not raining in Seattle. So 1 minus 125. So let's try to simplify this. So 0.25, 0.25, and the last term is 0.75. So cancel out, we get 3 here. And then apparently all of the denominators can be canceled out. So they are all 3 to the 3. Okay. So the numerator will become what? 2 cubed. And the denominator, the first term of the denominator is 2 cubed. And the second term in the denominator is 1 to the 3 times 3. So it's 3. So the answer is 8 divided by 8 plus 3, which is 8 divided by 11. All right. So see, this question is a little bit tricky because the condition has 3 events, y1, y2, y3. Also, it's very crucial to define the events very clearly. For example, y1 is the first friend said it is raining in Seattle. It does not mean that it is actually raining in Seattle. It does not mean that the first friend was not lying. It's just a fact. The first friend told you that it is raining in Seattle, etc. After you define the events very, very clearly and carefully, then you can answer the question easily. And we also assume that the friend's behaviors are conditionally independent. It's not written in the problem, but we have to assume it in order to solve the problem. Alright, that's all for this video. In the next video, we will review counting techniques like combinations, permutations, and also we'll talk about a few interview questions in data science. Thanks for watching. See you next time.